Since we have a small group, like let's keep this very dynamic. Like if you have questions, just get my attention, and then we can discuss. I'll try to fit in like within an hour, but so I might go fast on some slides and then slow down if you have questions. As I said, I've been working on Kudu for 2 years now. It's been open source only for 2 months. I can definitely answer pretty much all the questions that you might have about the product and the code. All right. So first, why Kudu? Right? A few years ago, we had a discussion at Cloudera, looking at the landscape, like what's missing, like where could we improve that, where do our customers experience the most problem. What's working well right now is on one side you have HDFS. So let's say using Parquet, you can do really fast batch insert jobs. You can do really quick fast analytics using Parquet with some other query engine on top. On the other side, with HBase, you can do all your random reads, updates, deletes, and whatnot really quickly. Keep the data mutable, but not so fast on the analytics. So if you plug that into an x-axis, that would be like just no numbers, just like fast at random axis, and the y-axis here would be simply like sequential speed. You have HBase on one side, you have Hadoop on the other side, but there's nothing that's in the middle that kind of does both at the same time. So that's why almost 3 years ago we set out to build Kudu. It's something that we wanted the product to have high throughput for scans, to be really close to Parquet, within 2x of Parquet. So most of the time we expect we should be a little slower, although like there's some tricks you can play, you might end up faster. Low latency, so maybe not always as fast as HBase in all the cases, but like for a certain set of trade-offs, you should be able to make it work for your use case. We want to have databases like semantics, so we don't want like yet another NoSQL database that you have to understand its APIs. We've all been through this so many times now. Let's just use something that people know, and so we're like using something that you understand. Relational data models. So if you want to do SQL queries, Kudu won't offer a SQL engine. It's kind of a bring your own SQL engine kind of thing. SQL queries are made easy by its data model, but you can also do NoSQL style of access. I'm going to use a lot of HBase examples. I used to be an HBase coder. I still am, but I'm not working full time on HBase. Let's see if you want to do a scan, an insert, put, or delete. You can also do it directly in the code.
So if you are in the middle,
right?
If you are in the middle, don't you think?
In the middle.
Yeah, if you are in the middle, don't you think that you are not there and you are not here? So
we're almost as fast as Parquet and almost as fast as HBase.
Okay.
Within an order of magnitude, so that it doesn't become a problem. Like in HBase, yeah, you can do full table scans, but it's going to be really slow. So slow that people will try to do hacks in order to make it work. Like we've seen Facebook, in order to make their scans faster on HBase, they would try to go directly on HDFS and read the H files, which is HBase's file format. But then you have the problem, well, if you directly read from the H files, you're going to have to merge all the data because the data can sit in so many files, you have to merge it, and blah, blah, blah. Eventually you're back with HBase, except you re-implemented the whole thing.
Yeah. Well, Facebook can afford, but a lot of other people may not afford to do that kind of stuff. Yeah.
Right, so there are many hacks you can do, or just dump it in HDFS and Parquet, and then to do a dump of 90, then read it so that your analytics is fast enough. I'm going to talk more.
The worst of all is have 2 copies of it.
Right, so that's what's been happening.
But at a high level, maybe we can say we can do it later, is there's also opposite ends of the spectrum of how many instances you run, or how many nodes are involved in HBase, and you don't run the HBase across 1,000 nodes. Whereas
we are.
most people don't.
Yeah.
HBase tends to be fewer nodes. You have a vast map sections doing MapReduce or Parquet, and then you have relatively small number of nodes, which actually tend to be a different skew with a lot more DRAM
Yes.
running HBase.
Yeah, it's
So-
like people use it as an operational database and it has very different requirements from
So
just
for
like
Kudu,
data
where do you
sync.
see? Are you going to? Is Kudu going to? Which end of the spectrum is Kudu?
More like HBase.
Okay.
Makes sense. So another thing that was going on, so we have identified the space where we want to improve how people are building their architectures. We also have a changing hardware landscape. So Hadoop was designed for splitting disks. So you're expecting really slow random access because you want to save. On seeks. That's basically what you want to do. Now we're going to SSDs, and the seeks are basically free. So if you want to leverage your I/O, it requires a different architecture. I remember when Drew from Facebook did a test on HBase just on SSDs. What was the next bottleneck after I/O?
What was network?
It was CPU. So
They were
now
running-
that the I/O was so fast, like it was expected, you're expecting slow seeks. Now you push a lot of random reads, and the random reads all become free on the I/O side. What's the next level after that? It's like auto logging and whatever happens right above it. So that HBase wasn't built to read from SSD, so it's always going to be a challenge. So we want something that's able to leverage those SSDs, but also technology that's coming. You have the NAND flash or the X-point, 3D cross-point technology that Intel is going to release very soon. They've announced it a few months ago. We've been working with them for a year now to make sure that Kudu will be 3D cross-point ready whenever it launches. But basically to have non-volatile memory that can back your database in some fashion. It requires that for example, if you have a cache, you store the cache in DRAM, you're expecting it to not be there when you restart the whole system. Well, what if it could be there, right? It's very different how it works. The RAM itself is getting cheaper. Running a JVM on 256 gigs of RAM, I wouldn't recommend it personally. You're going to have horrible GCs. Well, so what can we do in order to circumvent that? So the next bottleneck, it's the CPU, and what we found is the current storage systems, at least in the Hadoop space, they were not designed in the most CPU efficient way. Any questions so far?
That helps if you have measurement cores. Yeah, that's speed up.
I mean, it's just like being able to extract more from a single core also. Like how much data can you read from this going through a single core, or if it's already in memory? Let's say the I/O was really fast, like run the basic on flash. You have to be able to CPU has to be able to keep up with flash itself. So if you're designing your system thinking that I/O was going to be slow, you won't be able to leverage the flash that now you have access to. Like our customers at Cloudera have been asking us, like, when can I use servers that have like 250 gigs of RAM and all SSDs for HBase? We're like, you might be wasting your money there.
More cores only help to us until about 8, and after that it doesn't help. There's other bottlenecks in there.
And for sequential access, more cores won't help a single reader.
So the JVM, you are telling the more memory system has the garbage collection takes more time. That's why.
It's always been a problem. And
that's where you are writing this in C++ instead of
exactly.
Java.
So the Kudu has been rewrote in C++ for. That's one of the reasons why we did.
And that's why the Spark people also, they are developing their own.
Yes. The Spark people are basically rewriting Spark in C++, at least the core components.
The memory part of it.
So what is Kudu? It's scalable. It's still in beta also. So what we've done now is we've tested up to 275 nodes, so it's like a 3 petabytes cluster. Small cluster, but to John's point, those systems tend to have fewer nodes. We're not having randomly accessible data. If you can get like 20 petabytes of it, that's pretty good. I've never seen that. Unless you're Facebook and you're like a Facebook Messenger, then yeah, you have a lot of it. It's a lot of emails. But it is designed to go up to that scale. It's pretty fast. You can do millions of read and write operations across the whole cluster, or even within a single thread, you can do millions of operations per second. It's tabular, so it's in a format where your columns will. It's not like HBase where it's sparse. Your columns are predefined. They have a type, like any SQL database expects.
So those 275 nodes are having SSDs?
Sorry.
Those 275 nodes,
Not in that case.
those are all normal disks.
The normal, yeah, because that would be a pretty expensive cluster. You only have so much money to spend on test clusters.
Yeah. Basically, each node has 10 terabytes of storage.
Yeah, pretty much. I think it's 12, actually.
That's rounded down. Order of magnitude.
Do different APIs make a difference for the performance?
But
For example, C++ faster than Java. Well, you cannot use Java.
it's, Kudu has been written in C++,
C++.
and we have a native Java cluster. Our clients are fat, so they need to know things about the cluster. It's not just a wrapper around it. It doesn't just send strings on network and then something else is doing the computing, understanding of how to respond to your query. So we have fat clients in Java that speaks the native RPC protocol. We have also obviously a client in C++, and we have a Python wrapper like in Python around the C++ line. But it was done more like if your applications were in Java, you might as well go with the Java client. If you want to do, like we're expecting a lot of systems like Impala, which are written in C++, to simply be using C++. So like I said, the tables, they have a SQL-like schema. You have a finite number of columns, you can always alter it. It's going to be pretty quick, like in the orders of hundreds of milliseconds or seconds, not like a full day to drop a column or add one. All the types that you're expecting, we don't have the nested data types yet, although you could store them in a binary field, except you won't be able to do nifty things like introspecting your nested data type. We also have the concept of a primary row key, so unlike in HBase and Cassandra, you don't have like a special key that you need to build yourself. There's a lot of discussions in the HBase world around like crafting your row key and having the right schema for distribution and whatnot. In Kudu, we're more back to basics, so you're going to define columns that have a type, and you can say those columns together, they're your row key, and then we have uniqueness around that. We have, like I said, the Java and C++ NoSQL style APIs. We have a lot of integrations. The first one we built
Cassandra has the primary key concept, right?
Yes, yeah, like HBase. But like I said, you have to. In HBase, it's less important because like they usually hash partition across the cluster instead of using the total order partitioner. Like they have the murmur hash partitioner in Cassandra. But you can also do total order. So in HBase, it's always total order. Like the whole table is sorted. It's sorted based on the primary row key. Same thing in Cassandra. So depending on what your row key is, then it's going to go to some region in your cluster. So building the right row key becomes very important. If you have if you use the equivalent of an auto increment or just a timestamp, well, you're always going to be writing in the same region, so that's the same machine. And then that workload is going to move across the cluster, but always the same place. One solution is just to hash it. So in Cassandra, that's what they do by default. Their total order partition has other problems.
This is a hard question. What about like fault tolerance?
Getting there.
Okay.
It's just at the beginning of the talk.
Okay. Well, it's, at a high level, you say it's SQL-like schema. Where is it not like? Where is it not SQL?
Oh, okay. So we don't, like for example, we don't have relations. We don't have foreign keys.
Okay, but are there other cases of SQL? The things I worry about that's SQL-like, or many, is where does it? What things are things you can handle but run terribly, like some cardinality operation, or some there's use cases where it runs, but it's slow, incredibly slow commands.
Yeah.
I mean, there used to be things like don't use a less than operator. Where go back a few years, where the thing it would work, but it would do full table scans to do like a less than.
Yeah, so the thing is, we're assuming most of the time you're going to be doing full table scans with a fairly selective, selector. So you're gonna say like I select all the rows that are like this column is this value and this column is greater than this value. Like so, it's analytics on all your data most of the time.
Okay, so you're not trying to optimize out, like a pre-computed.
No, definitely not. We're not.
So no pre-computation at all.
So it's very much Hadoop-like in that regard.
Okay, so you're comparing this against something where, in general, you're doing full table scans on every operation.
Pretty much, yes. Ideally, like we were going to do is, we're more like an MPP database. Like if you put Impala with Kudu together, it's more like an MPP.
Yeah.
So, like we're going to do partition pruning if we can. There's a lot of like those kind of advanced optimization that are missing right now in Kudu.
Okay, so that's
like co-location of data between tables. Like
okay. So pretty much every command is a full table scan.
Yes.
A parallel one, but
yeah, exactly.
Right.
So it says integration with MapReduce, Spark, and Impala. So do you have integration with Hive?
No, that's something that's on the roadmap right now. But that's something. So that's funny. That's one thing we were assuming people were not going to be like asking us about Hive so much, and then we were at Strata in New York when we launched in September, and then everyone came and were like, "So do you have integrations with Hive?" And we were like, "No." with a Spark instead. So that was a discovery for us that people actually do a lot of like big ETL jobs in Hive, like really long-running jobs, and that's something that's hard to do with Impala or Drill.
Yeah.
So for those use cases, yes, we're going to need a Hive integration.
So when you say Spark integrations, what part of Spark? I mean, is it Spark ML? Is it PySpark?
Spark SQL, mostly Spark SQL.
Well,
right?
then you didn't mention Scala, so is it PySpark?
So we're. I have a few slides later.
Okay.
Actually, one slide. I can answer right now since we're on the subject. We have basic integration. It's in the works right now. It's basically a lot of syntactic sugar on top of the basic APIs, integrating with streaming and SQL. That's it.
Okay.
See, the reason I asked Hive is that whoever is running Hadoop distribution is not only Cloudera, there is other distributions also.
Oh, really?
Right? So, I'm hoping, right, you include Hortonworks also into this. Because if I write a tool or a product that takes care of, that uses Kudu, that means I can only sell to the people who are running Cloudera distribution.
So Kudu, I'm getting ahead of myself here, is Apache.
Yeah, I know.
Incubating right now. Yeah. So it's up to the vendors to pick it up and put it in their distribution. But to be very honest, we've been in contact with Hortonworks from day one, saying, guys, if you want to adopt Kudu and put it in your distribution, we're all in. We're going to help you.
Yeah, that is very much needed.
But,
you can differentiate at a higher level, but this seems to be a lower level, right? So
well, as long as it's Apache project, it's Hortonworks customers that will pull it in.
Pretty much. If their customers ask for it,
Yeah, and if their customers
well,
don't, they're not going to do
there
anything.
are many Apache projects where Hortonworks supports some and Cloudera supports
Oh, I know,
some.
but
So,
it's customer driven, their customers.
But our philosophy at Cloudera is that storage is always open.
yeah,
We're never going to lock in your storage.
yes.
You're there as a
Yeah, that's where I think if you both collaborate, because it's still lower level,
Yeah.
you can compete at higher levels.
I've
would be-
done that a lot with, when I was working on HBase. They have also a sizable HBase team at Hortonworks. And
Right.
like I've had a lot of meetings at Hortonworks to talk about HBase.
Right.
And they come to see us too.
Yes.
So yes, we're competing at that level and we're working hand in hand at the lower
Yes.
level. Alright, so the use cases that we're looking at. It's best if you have a combination of sequential and random. But your random should be not so much updates, like you're not supposed to be using like an update heavy. If you're rewriting the whole data set every day, running all the rows, Kudu is not a great fit. It's a great fit if you have a time series database. So you're always inserting data that's coming in. You might have to fix it. So let's say like, okay, I've got all the data from yesterday, but then there was one straggler machine that I couldn't, like I'm using Parquet and I'm creating partitions per day. the straggler machine came a few hours late. Now I have to rewrite the whole partition just to insert that missing data. Or maybe there's a data point that's wrong, and I need to update it. Well, if you're using Parquet, then you gotta do an update in place because it's write once, read many. So this is a perfect use case for Kudu. If you do a lot of sequential scans, sequential inserts, some amount of random reads, and then you have those odd inserts and updates. Perfect.
So this is where I'm still struggling with the current use case I'm working on, where we have the relational database, and they want the changes that are happening in the relational system to be reflected in the Hadoop platform. So we did a lot of research and should we use Cassandra, should we use HBase, should we use Hive, how do we do it? So finally we are using a CDC tool, which we tried Golden Gate, at Unity both, and we are doing a POC at Unity because there are still few things.
It's expensive.
Expensive is one part, and it's not fully finalized product. So they are writing into HDFS whatever changes that are coming in. Then we are building a view to take the historical data and the new changes and giving the final.
Yeah, I've heard that a lot before.
So that is the only thing that because we are not able to update a single record. We tried with Hortonworks. They have some ORC and you have to bucket it and you have to do various things. But each update is taking a minute.
Yes.
And there are 100,000 updates are coming every day. So it was practically not usable. It seems to be this one is better.
It's the right thing. So I think CDC should be one more use case. It's also some discussion we had internally last week that they're starting to look at CDC and say like, hey, maybe Kudu is actually a pretty good fit for this too. The hard part is the middle, right? It's getting the data in a reliable way on the other side and representing all the changes.
I'm giving feedback to these vendors. Write into Kafka. Don't write into Hadoop.
Exactly.
I will take care of it. How to write into my stuff. Write into Kafka, then I do Spark streaming, take it and do the update here.
It's more complicated than that, right? There's some transformation also. Long time no see.
Yeah, how's it going? Sorry, shouldn't forget.
We used to work together at StumbleUpon when I was working on HBase.
It's been a few years. 4 or 5 years.
Good to see you.
Yeah, good to see you. Catch up later.
Ciao. Alright. So yeah, CDC, good use case. But the hard part is also in the middle.
Yeah.
That's why you look at those expensive solutions. Let's move forward.
Sure.
So those are the use cases. So now, if you're looking at what might be like the current architecture, what our customers, what the Hadoop community is currently doing. So let's think for a use case that's fraud detection. You're going to have all the incoming data on some messaging system that's going to be dumped into HBase because it can do those random updates, random deletes, random inserts, but it can also handle the sequential inserts. And then you can dump all this data into a Parquet file, and then the Parquet file eventually, at some point, will be loaded into HDFS in a volume. You have to reorganize your partitions and whatnot, and then you can do reporting. So what this means is that the most recent data will never be available when it comes in. It's going to be available sometime later, minutes, hours, days, maybe. And you have a lot of moving parts that you have to make decisions. Like, so what are if I want to get my data right away, that means that I'm going to do a lot of inefficient things. And the longer you wait, the more efficient you're going to trade-offs. And you have a lot of moving parts in there also, moving from one system to another. So what we're trying to do with Kudu is you replace the whole thing, the whole Lambda architecture, and you just put Kudu in the middle. You write to Kudu, you read from Kudu, that this is how we want to solve your problem. So you have one system to operate, only one system to understand. You don't have to deal with a bunch of cron jobs that do the data transformations from one system to another.
Can I get away from having a landing zone on this?
I think if you can directly write to Kudu, then you don't need to. But I would say that's a problem that's kind of outside the scope of the product. That's cool.
Well, in your show me example,
This example. I can go through the example and then.
I'm just trying to figure out in the writer case, does it effectively end up serializing the writers because I've got this app generating events.
Yep.
Or I've got in this other case, I've got 100,000, tens of millions of people generating events. But a lot of times you end up having to put it through a gateway system that effectively serializes it because it's got to take events from one source and put it into, in this case, Kudu. One of the things that's been an issue is being able to, in some trusted way, just call an API from something that's outside the cluster and be able to write this stuff directly into Kudu, for example. I'm just trying to figure out if that's part of Kudu or it's considered outside the scope.
I mean, figuring out exactly how your gateway functions.
Well, I'd like to get rid of the gateway, to be honest. That's the.
Well, you can have a Kudu client sitting directly at the gateway. That's going to insert.
And the Kudu client does not have to be part of the cluster.
It doesn't have to be part of the cluster. Yes, that's.
Okay.
It directly contacts the node that you need to talk to store the data. So it knows about the layout of the cluster, and it can write directly to it.
How does it find out about the layout? If I'm not part, okay. We understand the source of the question is.
Yes.
There's bootstrapping problems. How do the clients know where to write if they're not part of the cluster?
So just to show the simplification of the Xiaomi Big Data Analytics pipeline. So before Kudu, they had data source either writing to HBase or using Scribe to write sequence files. So Scribe was a project from Facebook and basically able to dump a lot of data in parallel into HDFS. Eventually, they all went to Hive, MapR, Spark, MapReduce, Spark. If you want to do offline analysis, that you can do it directly in Hive, and then you have reports, or maybe you want to do some interactive real-time analysis, so you go to a different pipeline that would be HDFS Parquet, and then you put Impala on top, and then you can do your analytics curves. So in their case, they had high latency getting access to their data. 1 hour to a day. A lot of conversions of data between all the different systems.
So these are all time series data, is it?
Sorry?
It's all time series data.
Yeah.
Their own insights.
Pretty much, yes. So with Kudu, they have two pipelines at the beginning. They can directly ingest into Kudu, or they can go to four pipelines that need to be just that don't mind the back pressure. But if you're expecting a high load and you're expecting some back pressure because it just happens that the system is getting a lot of inserts, then they go from Scribe to Kafka and then to Storm. You could also use Spark Streaming here, Kafka to Spark Streaming, and then directly lands into Kudu. And then from Kudu, they read from Impala if they want to do some analytical queries. If they just want to do some random access, just directly talk to Kudu. There's no need to go to different systems. Kudu can field both. So their pipeline, it goes from 0 seconds. Basically, as soon as your data is available, to 10 seconds, it has to go through the ETL way of Kafka and Storm.
So when you say back pressure, what do you mean?
What I mean is let's say you just have a high volume of data that arrives all of a sudden. Obviously, you only have so many IOPS, right? So you might have to buffer in memory a little bit. That case.
In that case, you go to the other road.
So it's going to stay in Storm, and then Storm is going to dump it into Kudu
Whenever.
as fast as it can.
Almost like queuing.
How it works. So your tables, if you're used to HBase and other similar systems like Bigtable, so we're using the table and tablet instead of region parlance. This is the same word that they use in the Bigtable paper. Your tables, they're horizontally partitioned into tablets, either range or hash partitioning. You actually have a choice here. Range would be like HBase, hash by the default in HBase, hash would be the default in Cassandra. You can do both. And so using some SQL-like language here, that would be in Impala, you could say, okay, this is going to be my primary key, host metric timestamp. And then distribute it into so many buckets. Each bucket would be a tablet. And this is how you get the distribution of your data in your cluster.
So how do you know when I'm creating a new table? How do I know how many buckets it should go into?
rule of thumb, like 10 per server. Each tablet will be replicated using graph consensus. So since Kudu doesn't use HDFS, you can just use Kudu directly on your on a machine on a cluster that has nothing else, just Kudu. And it's going to use either ext4 or XFS for the storage. So the replication has to be handled somehow. So it's through logical replication using the graph consensus. So if you're familiar with etcd, you're also using graph replication. So it's baked into the write-ahead mode. So when you write, you have to write to, if you have a form of 3 nodes, well, if you have a configuration of 3 nodes, you need 2 nodes that say yes, and then that's how you get your write accepted in the cluster.
Can we collocate Kudu and HDFS at the
Yes.
same time?
Actually, all our testing internally at Cloudera has been on nodes that had both Kudu and HDFS, and running MapReduce between both of them.
Okay.
Or joins in Impala, joins of Parquet files with Kudu tables.
Oh, nice.
Before you go, what do you do if there's like, for instance, there's joins on Kudu tables and HDFS? If the wrap consensus isn't matching for some reason or another.
If it accepted the data, it's going to match.
Okay, but like,
But there's a clear separation between HDFS and Kudu. So
what I'm
whether
saying
it's in the context of a join between the two, that will happen in a higher level. Then it's like Kudu.
so like the wrap consensus on the previous slide, that occurs entirely within Kudu.
Yes.
Okay.
In between tablet servers. So a tablet will be on 3 machines.
Yeah.
And those 3 machines run the graph consensus algorithm. There's going to be 1 leader followers.
Okay. So one of the, I don't know if you've read the Cockroach DB.
Very
Okay.
familiar with this.
So if you're running a wrapped consensus algorithm for every tablet, and you have vast numbers of tablets, machines are going to overlap and the communications go up.
So
Well,
their
they go-
design assumes thousands of tablets. Our design assumes tens, if hundreds.
Okay,
So it's different orders of magnitude.
so at the level you're at, you don't see the need to do coalescing of communications between, like,
We don't see it. Right.
okay,
So all the metadata for all your tablet servers, they're kept inside the master. So against the old master-slave architecture, like the name node in HDFS with the data nodes, like the HBase master with the region servers. So we have a master. It's replicated using graph consensus. This is a repository where you bootstrap the clients from, and where you post all the information about the knowledge of the cluster. Where are my tablets? Which tables are available? What's their schema? And the master has a few light responsibilities like load balancing, handling the creation of new tables, handling the deletion of a table. It's fairly small data, so it's just basically always cached in RAM. And so when you want to bootstrap, you're going to configure the client with the master addresses, going to figure out the leader, talk to that leader, say, hey, where's my data? You get information, then you cache it. So what this looks like, this would be a cluster deployment. So you have a client that's metadata cache on one side. You have the master tablet, which is the master role on the other side. That's replicated. And then you have a bunch of tablet servers with tablets that are put on those tablet servers. In packs of 3 in this case, you could have 5. You could have 1, except you won't have any guarantee that your data will survive the machine failure. So 3 is the usual that we've been testing.
The master tablets? The master tablets?
Oh, it's all wrapped.
No, the 3 is what?
3 is wrapped. So both the master actually inside stores it's in a tablet.
think of them as a mini cluster for one
Yeah,
cluster
they have
per
their own
tablet.
mini cluster with their own tablet that they all share.
So
It's a special role.
okay, so the reason why I think I'm trying to wrap my head around is, say I have 3 servers per tablet, and you're saying you're looking at a few hundred at most tablets, then I would never really have more than a few hundred times 3 servers.
You can have multiple tablets per tablet server. So like in the example here, tablet server.
Well, they can overlap, but
Yeah.
but you say you test. I'm trying to figure out why there are only a few hundred tablets. total?
You only have a few tables that need that level of replication.
Say I have 1,000 servers.
Yep.
And let's say I have 3,000 servers, just to make the math easier, and I'm using Trip, and I'm using a RAF level of 3. So that means I can, each server could, there's 1,000, there's room for 1,000 tablets.
Let's say you put 10 per tablet server. That means you can have 30,000 tablet times 3, that's 90,000 tablets.
Okay. It gets back to the thing about why you don't need to coalesce RAF communication. I think it's, you've tested this to thousands and it doesn't.
We haven't tested. It's designed to. The test, we've gone up to 275.
Okay, now I understand. So I think you're going to have a problem when you get to 1,000.
Yeah, I think there are some definitely some things that we'll have to improve when I go to that level. But the nodes are getting bigger. I'm not expecting to see a lot of cluster even in the 500 node range. Like especially if you put really expensive hardware,
I was just thinking about what the Cockroach DB guys hit, and they hit it much earlier than 500. Now maybe.
But that's because they're going to use 10,000 tablets per server.
All right. Let me think.
I'll
just think about it because that was a problem. The problem is the communication. So in that picture, if say server W has a subset of tablets, and but for every triplet, it has to do communication to two other instances of Raft. And if you end up having, if each server had like 100 instances of Raft running, they've all got to communicate with some other they overlap a little bit, but not in everything. So you have a lot of messages going back and forth.
Grows pretty exponentially.
Well, that's what the Cockroach DB guys claim, and I tend to believe them.
But as I said, they are using a lot more tablets for a small cluster.
For a small cluster.
Even for a small cluster, they use a lot of tablets.
They do, because they're doing it by a much more granular thing.
Exactly. I think it's in the tens of megabytes scale per tablet. Our tablets can be fat. Like, we've tested up to 4 terabytes per tablet.
Okay.
And that's just because we wanted to see, like, can we do 4? Yeah. With a few tweaks, we were able to get to 4.
There's no intrinsic reason why you couldn't use their code.
Yeah,
it's open source, both sides.
The thing is, for analytics, you tend to want to do like long IOs. So Impala wants to be able to read a lot of data and then like.
Yeah, this is just the RAF communication. There's nothing else. I'm just talking about the RAF stuff. Don't want to beat it to ground. I just wanted to. I'm trying to look. Like I told you at the beginning, where this breaks at scale, what number, and what's going to run out. RAF is kind of.
It's chatty.
Yeah, it is.
The master table is covered with metadata.
Yep.
So you're caching.
Yes, in
That's
RAM.
why faster than actually.
No.
This is also distributed.
Yes,
So
I'll
then the seamless between
same as I explained that.
is like faster than
It's at the lower level that's different. I'm currently at the high level, and you can go down there. So simply, like, let's say you want to, hey master, where's the .lipcon for table T? So the master is going to reply, it's part of tablet 2, which lives on those servers. Also, by the way, like, here's more information about some of the tablets, so you can pre-cache, and you don't have to do more round trips, like for the next chunk of data that you want to get. So then the metadata cache gets populated in the client, and the client can say, okay, hey, tablet server 2 talks to the leader. The master will try to give the latest leader. It might not be up to date, so it might go to a tablet that's not a follower. It's going to say, hey, I'm not the leader anymore. Talk to this guy. Then you get the right person. Say, update this row for this value. And it just works.
If you have a stale cache, it'll give you a referral, or it'll tell you to go back to the master.
Referral. So RAF consensus, a bit lower level. So you have the client that talks to the tablet server. It's going to do a write RPC. In parallel, it's going to write to its own write-ahead log, and then it's going to send RPCs to the followers in parallel and say, please update your consensus, let's move forward. In parallel, those, or not, if one of them is dead, they're going to write to their own write-ahead log. Then one of them will win and will say success to the leader. The leader has achieved majority, it has itself, plus one of its followers. The other one will arrive at some point. And so you can reply to the client, success, your write has been accepted, it is persistent.
Do you acknowledge before the write-ahead log is done, or after?
After.
After all of them? Or any two of the three?
Is it similar to Kafka?
Kafka has 3 modes. So Kafka gives you a knob. That's why I was asking the question.
Kafka has the partitions, right?
In this case, you have to have quorum. So a quorum of whichever ensemble. So if you have an ensemble of 5, that's 3. If you have 3, that's 2.
So the Raft is it similar to Zookeeper?
So they use they use Paxos. Raft is like Paxos made easy. That's how they call the paper. So
Is there
it's
any
the
reason
same
that
paper,
you would
consensus
not use?
algorithm, but they have a leader that has responsibility. So instead of like trying to get consensus of all the nodes without responsibilities, there's one leader that has responsibility of moving things forward, and then the followers that just reply.
So that is the reason that you did not choose Zookeeper and choose. So is there any reason that you chose this one compared to Zookeeper? That was the reason?
Much easier to use. Yeah, to implement.
Zookeeper is bigger than just a cluster consensus algorithm. Raft is nothing but a cluster consensus algorithm.
I think he meant like use Zookeeper's Paxos implementation, which is what is it called again?
Lamport. That's the Paxos.
No, but they have a special name. They published a paper about the Paxos implementation they use. So it's another flavor of Paxos.
That was like a Lamport.
I'm just asking because Zookeeper is already part of the distribution.
Yes. But we want to use Zookeeper itself. Using Zookeeper is meant for metadata, not like for storing your petabytes of data. That's going to be way too slow.
You are here also. So
That's why even Kafka, they removed the Zookeeper from consumers.
Yep.
Because that was very time consuming in this one. And it's good till a certain amount of data. If the data gets bigger, the Zookeeper expands exponentially.
Yep.
So you cannot have Zookeeper.
Yep, very good point. So fault tolerance, if you have a transient failure of a follower, so that means one of the 2 follower is gone for some reason, the leader can still achieve majority as soon as the other follower responds. If you have the leader that's gone, that dies for some reason, then there's going to be an automatic re-election of the leader between the 2 followers, and they can get a consensus because there's still 2 of them. If you restart a dead tablet server or the process or the whole machine or whatever, within 5 minutes, usually it's going to be able to rejoin the tablet quorum as a follower. It's going to be told like, hey, you're another leader, sorry. I'm the new leader now. Just please accept all my edits. And if you have anything that you wrote to your wall that wasn't like majority accepted, then you can flush it. Permanent failures, let's say you have a node that's just gone, then the master will pick a new node that's going to host a new replica. That replica will contact the leader, and there's going to be a remote bootstrap process which is going to copy all its data to the new node, in a streaming fashion. And then once it's caught up, then it's going to plug itself in the Raft consensus algorithm, and then continue receiving updates until it's up to you.
So one of the things where this breaks, like etcd breaks in these systems, is the time it takes to get a full copy.
Yeah.
So
we actually had a bug actually last week where we didn't test like what happens if it takes more than 5 minutes.
That's why I was asking the question: is have you done? It's a standard thing that breaks.
Yep.
So is that your model that you have to be able to get a copy of a tablet? A tablet cannot be larger than what it takes to actually get into sync in 5 minutes.
So it's a bug that kind of there was just a timeout somewhere. Hey, if it didn't see the new tablet within 5 minutes, then it was going to pick a new replica and start the process all over again forever.
Yeah, and that's actually what happened. If you remember that Amazon outage with about a couple months ago, that was morally that.
Yeah, that's an easy one. So we didn't track progress. Like, oh, are you making progress? Copying my data? Then I shouldn't time you out in 5 minutes.
Okay, so there's 2 ways of addressing this. That's what I'm trying to get to is you want to make a tablet size capped by what you can transfer in a certain period of time, or you're just willing to wait as long as you're making progress, you're just going to keep going forever?
That's a good question.
Because that's usually a block in a scalability problem.
Yeah.
It's also one of the reasons why things like Raft generally should never use 3. You should always use 5. Because if you use 3 and 1 goes down, You pick a new guy, but if he
What's the
takes
core?
half an hour to get into sync, he's not usable, even though he's part of the cluster,
Yep.
but he's not, and he can't take any operations.
Yep.
And in fact, you still have a single point of failure that can go on for a really long time.
Because if you lose another one, even if you have one remaining,
Yeah.
you got it even right.
And that's one of the reasons why we always have to use 5. Like with that CD, if you don't use 5, you're going to be in trouble.
Yeah, if you're really high voltage, yes.
So you've hit that bug in practice. Are you going to err on the side of making larger and larger tablets?
It's going to be a good, interesting trade-off. Since we haven't had so much of the experience yet, like I can tell you that the solution to the 500 timeout is start the timeout when the node stops making progress, copying the data. Like as long as it's copying, and then there's the question of like, is it copying fast enough? Is it copying as fast as it should be? Am I hitting a slow node? I think the devil's in the detail, and there's going to be a lot of time that will have to be spent like perfecting that area. On the 5 node replica thing, right now we're recommending 3 for just one cluster, since like it's pretty easy to, especially if it fits in a single rack.
3 is all you need except for this problem.
Yeah,
And that's why the only reason to do this is because of this problem.
but it's also designed for multi-data center, which we don't really support right now. But in the case of multi-data center, then you really need 5. Because you're going to be putting like 2 in one data center, 2 in another data center, and then like a tiebreaker in a third data center.
Yeah.
I'm going to be making progress since, in theory, I have 4 minutes left in this presentation, and I'm not even halfway through.
Feel free to go on as long as you have to. I think this is very valuable.
Are you finding this valuable?
Oh yeah.
I'll stop asking questions.
More questions.
So, Kudu uses a columnar storage, so that means that all your columns that have been predefined will be stored separately. So when you access them, you don't access all of your rows, all the columns in your rows.
One quick question. The problem with columnar database is that you have to have all your data to create that block of your Parquet block, right? Or whatever that. I'm just trying to compare. So you have to have the whole data to make it a complete set, right?
That's not a problem. So here it's more like HBase, where you write in memory, append to the write-ahead log, and it's queryable in memory. If the machine dies, we replay the logs, and you're back to you still have your data.
No, I'm getting to from the disk point of view. So when you write to a disk, right, you have to have the whole thing, all columns well defined to do this kind of work. Because you write the data of each column in one single location. Whenever you're writing in a disk, it becomes a serial kind of thing, not a columnar kind of thing, right? That column A, then column B, then column C. That's how you write on the disk.
What we write on the disk is going to be column A on some disk in some place, column B on some disk in some place, column C on some disk in some place.
Okay, it's not on same location.
No.
Okay.
So that's the whole point of columnar, is each column is stored separately. Like if you were to put them all next to each other, then you're row-wise instead of column-wise. So in the Kudu case, like you're gonna have, like here your row key would be the tweet ID if you're using the Twitter firehose table, and you're gonna have other separate columns for all the other files for all the other columns, which might be all of very different type. So let's say you have all your different files on disk. You want to do a const star where username is something. It's not even the primary key here. So you only need to read that one column, and you can do a count of all the rows, but only for that one column that matches. You don't need to read the whole thing to say like, yes, this row exists. The row exists if there's value in it.
And so this is the value proposition. That's why it's so fast.
One of the reasons why is, like, for analytics, usually you need columnar, and so the counter argument would be, yeah, so if I want to read the whole row, that that means I need to seek in all the different columns to materialize the whole thing. But since we're assuming people will be moving more and more toward SSDs, the seek argument is not as important as it used to be when you had the spinning disks. Yes.
Does the Kudu have a shell like file system shell like HDFS shell?
No.
So
No, because like it's very opaque actually the way we store data. Like we create big containers of blocks that are all 32 megabytes, and then we just fill the containers with blocks from any table, any tablet. It doesn't matter. It actually doesn't.
The reason I asked is, you have a truncate operator, which means I have 10 million rows.
Mhm.
Instead of deleting one row at a time, I can go to a file system shell and delete all the files. And
Well, what if your row is like in all different files, but it's not the whole file?
yeah, so
So you would do that through the API.
That's it. You say use the API, don't go to the back door.
But we are that's something for version 1.0 for GA that we're exploring is being able to, if you partition your data in a way that like every day you create a new partition that will be a tablet, and you want to get rid of some tablets to be able to just like drop a whole tablet and that will just do the deletion of the blocks on the file system. There are some tricks you can play. So columnar compression, since we know what kind of data you're storing and we're storing it together on disk, we can be very good at how we compress it. So let's say you're using the created at, which is a timestamp kind of column. Well, we can do just a diff compression. So the first value is going to be something, and then you just store the difference. So instead of using the 64 bits, you're only using like 70. So all those columns from many rows, because it's all the rows that are like we're not just like storing the data for one row in one file. It's like all the rows in that tablet. We're going to store the data from all that one column next to each other. So since they're all the same type, compression can be very effective. So if you have the time series value timestamps or strings that always repeat, like you always have the same 8 strings, your data basically won't use any space on this.
So
And that's also something that Kudu does way better than HBase.
So one thing that I want to know, now that you store one column in a block, how do you have the row thing? You keep the primary with every
We
column?
use an ID internally. So we actually chunk up the tablets in what we call row sets. And a row only belongs to one row set at a time. Those row sets are going to be around 32 megabytes. So you're going to have like as many row sets as you need for the whole tablet. And within each row set, we're going to have a special index. That's the row key index.
Okay.
So when you store the values of each column, you store them along with the index.
One more question after that.
That's
when you say the row key index, can we just make sure that if we access that row key index and do some kind of an computation,
you don't have access to it.
I won't have access to it?
No, because the index is only relevant within the row set itself, and you're going to have thousands of them, so there's going to be repetitions. And so it's a very specific implementation detail inside the tablet. So getting the numbers back would be nothing from like the high level point if you're just looking at your data. It's an optimization on how we store the data using some sort of index, some number, instead of maybe storing like one big string or whatever, like HBase does. So HBase, like along each value, you also have to have the full key, the full row key. Let's say your row key is always like 30 bytes. 30 bytes plus the family, plus the qualifier, plus the timestamp, and maybe you're just storing a boolean, So you can have like 50 bytes for, 1 byte because you can't store less than that. That's another thing in HBase that happens. It's sparse in HBase. That's how you do it. But there's stuff like that you can't do. That's a trade-off in Kudu. So how we handle inserts, we're expecting something. We're always inserting. You're sometimes updating, sometimes deleting. And if you do want to do bulk deletes, eventually we'll have a fast way to do it.
I'm fine with it not being fast if you do lots of updates, but it needs to not break. So it's fine if it slows down if I do something bad,
Right,
It
it's gonna
can't.
slow
It
down.
can't die.
It's gonna slow down. And we do gradual pushback also. Like when we see we're like past a certain point and we're getting eventually close, and we're gonna randomly start sending clients back instead of accepting their inserts.
But it doesn't fail, right? If there are a lot of updates, let's say
The
batch,
client will just retry. The client will get like, I'm too busy. It's gonna wait a little bit and then come back.
because there are some nightly jobs that are pumping a lot of updates.
It's same
There
with
are-
inserts and deletes, right?
Pardon?
Inserts, they go in the memorial set, but they also use memory. Deletes, they go in the Delta mem store that uses memory. And you only have so much memory. So integrations, here's an example. If you want to use Spark SQL with Kudu, you're simply going to register, you're going to have a SQL context that's going to be derived from the Kudu context. And you're going to do some sort of mapping. This is where this is the table I want to use. This is where my master is, and then directly do the SQL on top of it. And the transformation will be done in the background. So what's nice with the data frames in Spark is they're typed, so and we're typed also. So if you match the types, it becomes pretty natural. Unlike HBase, where you don't like, or in Hive, if you want to do Hive on HBase, you have to define types, but in HBase, it's just bad arrays. So it's not very interesting. We also have an Impala integration. So one thing that we didn't have in Impala before was insert, update, and deletes, doing that in a random fashion. So we had to augment the Impala SQL language to be able to do those operations. And we do there's a lot of things. We're doing a lot of things already to make it fast, but there's a lot of other things we can do. For example, using shared memory between the Kudu clients, which resides inside Impala, and the tablet server that resides on the same machine. So instead of having to go through a socket, you can just basically directly read from the tablet server's memory. And if you're using Impala, Jeremiah, they're working on a drill integration also.
Could you explain that again? How does it go without the socket? How does it read? Is it?
Oh, it's not something that's there. I'm just saying that's an optimization that we have like in the works using shared memory.
Okay.
I'm not privy to the details of how shared memory works, unfortunately.
So when you create a table in Kudu,
It
where
doesn't
does
become available immediately. Kudu doesn't know about Impala. So in Impala, you can create external tables. That's a table that's already created in Kudu. It's going to load the schema and use the table as is. Just won't be able to drop it. Or you can create a table stored in Kudu in Impala, and then so Impala will create the table inside Kudu, and then be able to use it.
let's say Impala is not there in the picture. When
Yes,
you
so what-
let's say Impala is not there in the picture. When you create a table in Kudu, where does it store this metadata of this
Master.
table? Okay.
So the
So
master has all the schema repositories and the table repositories, the tablet repositories. So in the Impala, if you create a table, it's going to have its own metadata in Hive also, in the Hive metadata server.
Right.
Twice. Although in the Kudu case, like you have the actual physical location of everything. Whereas in Impala, you have basically a schema and where the master is.
so you don't need a separate RDBMS like MySQL to store the schema.
Not if you just use Kudu.
Right.
If you use Impala, which relies on Hive, then you need the Hive
Yeah,
server,
meta storage
which relies
based on
MySQL.
some RDBMS. Yeah.
Exactly.
But here you don't need any external RDBMS to
Not
store
if you're
this.
just using Kudu.
Yeah.
Kudu is its own dependency.
Yeah, I'm using Spark and Kudu. I don't need any external.
Exactly. Yeah, you could just have Spark and Kudu also. That's it. No HDFS, no MapReduce, no whatever. We also have MapReduce integration, so the very basic stuff like an input and an output format. A few jobs like count all the rows in a given table. Very, very plain MapReduce. Performance. When we released Kudu 2 months ago, we did a TPCH benchmark. So we used 75 servers with 12 spinning disks each. And we ran a scale factor of 100 gigs. 100 gigs, 75 machines. The data set fits in memory. So this is the results we got. So on the x-axis, it's the query. And then the two colors, kind of blue is Parquet, kind of orange is Kudu. And on the y-axis, you have it's the latency.
Latency in
There's a spelling mistake. It's not
milliseconds.
linear.
That would imply that it goes up to 45
There's a
seconds.
C missing. Anyway, it's in milliseconds, so it goes up to
45 seconds.
45 seconds.
So why did you test the span disk if this is really an SSD type?
That's what we had.
I think it's for a lot of like legacy systems.
Well, you designed a system for basically IOPS being free, and then you tested on spinning disk. That's what I was asking.
Yeah. But in this case, it's an analytical query, so you're expecting long reads. So it's actually should be faster on spinning disk than SSDs.
SSDs are faster than disk now.
Even for sequential reads, things are getting better. So that's what we had, like at some scale.
Okay.
So in most cases, so the higher it goes, the worse it is. So you'll see in a lot of cases, Kudu is actually lower than Parquet, meaning it's faster than Parquet. In those cases, oftentimes, because it was a pretty selective predicate, that we were able to push all the way down to the server, so we were able to read a lot less data than Parquet, and it's all about the data we read, how fast you're going. It's also a case where the data fits in memory, so if we redid the test like with a much higher scale factor that had to hit disk, then Parquet, in even the cases where we can be pretty selective, might still be faster, simply because it can do really long I/Os, like read 8 megabytes of data in one shot. Whereas in the Kudu case, we're always reading in small blocks of 64 kilobytes. So then it's gonna, like the fact that you're hitting this is really gonna show. But it was a pretty good test. Like it meant that we're in the pretty much in the ballpark that we wanted to be. How we compare to other NoSQL storage. So let's say you want to use Phoenix because it has a SQL layer on HBase, and then compare it to Impala plus Kudu, and then run exactly the same queries in both systems. So we use a small 10-node cluster, and we use like only 6 billion rows. Only had so much time to run the test. Like loading the data was actually the fastest was in Parquet, and then Kudu Impala, and then Phoenix HBase comparable. So here, if I remember correctly, it's in seconds. So like it took 2100 seconds to load in Phoenix, 1900 to load in HBase, and it's also log scale. So if you run the TPCH query 1, no joins, simple select from where, you can see 200 seconds in the Phoenix case, 13 seconds in the Kudu case, and 9 seconds in the Parquet case. So Parquet and Kudu in the same ballpark. The Phoenix plus HBase is way higher.
Because of a lot of range scanning happening here.
Well, Phoenix had, because it's using HBase, it has to materialize all the rows because it's using only one count family in that case. So there's a lot of things that are not as efficient. It's a lot of numbers also in number 1. So we can do a lot of really smart compression that HBase cannot do. Now, like a query where you just count star, that's kind of cheating because in the Kudu case and the Parquet case, we just read metadata in that case. Whereas in HBase, it actually has to materialize the whole data set in order to count it. Although it uses filters, tries to do a few things, but it does have to hit this. So 76 seconds to count star versus a second something for the Parquet and Kudu. The count star where some selection happened, it was even slower. This one I'm not sure about, the numbers look kind of weird. But the single row lookup, that's the case where Phoenix was faster than everything else, and that's also expected. Where HBase is going to be almost as fast as Kudu is going to be almost as fast as HBase in the random lookup case, and like it was like 40 milliseconds, still slow through Phoenix to read a single row, and it was 150 going through Impala and then Kudu to reach your data. And then if you just went to Parquet and tried to get one row, it was a second per step. Xiaomi did their own benchmarks. So they have a few queries, like the kind of stuff they run in their application. They're like, okay, let's compare what it does on Parquet versus what it does on Kudu. So kind of the same test here. You're using your application 3 in both cases, and each query ran 5 times. Then you took the average. So latency, except for query number 1, HBase was basically faster for them on Kudu was faster for them than Parquet in almost all cases. And it was for, don't mention the data set next slide, unfortunately. And finally, we did a NoSQL style random access comparison between just YCSB against HBase, YCSB against Kudu. And just to show you that, like, we're not hiding the fact that we have trade-offs and we might be really slower for you. Again, at the same 10 node cluster as before, 100 million rows, 10 million operations. It's the throughput, the number of operations per second. So the farthest on the right you are, the better it is. And the red is HBase. So you can see that HBase wins every single case except one. It's on a Zipfian uniform distribution, where Kudu is barely faster, and that might just be because that's how it happened. You would run it again, and it might be like the other one will overtake the first one. So Zipfian in particular, like let's say you're running a lot of updates and deletes on the same rows, like in the distribution curve. It's going to be a lot more costly for Kudu to materialize those rows because it has a lot to apply on the updates. And also the same for inserts, it has a lot more to do. Whereas for HBase, when you update, it's just a write. You don't need to read. Kudu has to read online.
So you read it and then update it.
Sorry?
You read a record and then update it.
We actually need to know if it exists.
Okay.
Because we have the uniqueness constraint. So in Kudu, if you want to update, first we need to find your row in all the row sets. So we have a tree set. So we do some pruning, and then we have loop filters that we interrogate on every row set. We have that row, we have that row, we have that row. And then it might say, maybe. So then you actually read the index. Is the row there? Because the loop filter might, it might say maybe, but actually it's, until you find it, and then, well, maybe you're unlucky, and actually the row doesn't exist. So then you return an error. In the HBase case, insert, update, deletes, it's the same operation, it's a put. Because the row doesn't need to exist if you update. The update doesn't exist in HBase. Because you always rematerialize the row in the other. Alright, so finally, if you want to get started, so we open sourced our beta in September of 2015. We announced that we're going to donate it to the Apache Software Foundation. We started the incubate, we sent the discussion thread to the incubation mailing list in November, and the vote passed in December. So now we're officially Apache Kudu in parentheses incubating. We released the first update version, so 0.50 was the first version released. 0.60 released in November. Basically contains fixes that people have noticed when we released the software, but also it used to only work on Linux, now it also works on Mac OS X, although not for production. It's still beta, and it's going to be beta.
What is that? It was working on Unix, and now what?
OS X. Mac.
Okay.
So you can use Kudu on your Mac box, but don't use it, don't put a Mac server cluster running Kudu in production. There's a lot of things that are going to be missing.
One big question I always have in these things is when would you expect to make a stable API where you're going to preserve the API going forward?
That's for GA, that's within 1 year.
Roughly a year?
Yeah.
So until that point, existing APIs can change.
Yeah. We're going to do our best to not change it. Actually, between 0.50 and 0.60, there was one breaking change on the Java side of the API, but it was still wire compatible. So you can still run the old client versus the new servers and vice versa. And it was just actually a rename of a single class. We're going to do our best to keep it forward compatible and backward compatible during the beta. But
There is
guarantees will only happen at GA.
Okay.
We want to be able to iterate over the next year as
But there's questions when you set the contract of permanent API support.
in about a year.
Okay.
We want people. So what we're trying to get right now is not people running Kudu in production. We're trying to get stories. What kind of use cases do you have? Do you think it fits what Kudu offers? Are we actually solving a problem that you have? If not, are we very far out? Are we just missing some functionalities that if we had it, then it would definitely solve the use case? And this is what we're working on for the next year. But also, we don't have any security right now. So basic like authentication, encryption, vulnerability, all that good stuff. Like we haven't done anything.
Do you expect that will be a major API change then?
Yes, obviously there's going to be, well, if you want to use the unsecured version, no, but then there's going to be the setup of the Kerberos token.
And maybe not then a parameter on every call.
I don't think so.
Depends how you run it.
I know at least for HBase, like it wasn't a breaking change when they added security. Well, it was a breaking change for wire protocol, that's for sure.
Yeah.
But yeah.
So all your testing to date has been on spinning disk systems.
We just got a flash cluster, so it has one flash disk and 12 spinning disks.
So that's probably another thing you should be looking for, is somebody who can test this thing. I mean, one of the things where HBase is likely to break down, at least in my experience, is in terms of performance growth, it doesn't really take advantage. If you have a machine full of SSDs, it doesn't get as fast as it should be.
No, definitely not.
And so maybe that's a place where you can actually pass HBase.
For
On
random
one
reasons,
system.
yeah, just because we can leverage it.
Just because of leverage.
Yeah, and also because we can allocate like a big cache, or even we found that the cache buffer, OS buffer is actually pretty good for us. Like you only require a small cache for the stuff that's really really hot. The rest actually can sit in the buffer because we don't have we don't go through HDFS to get to the data. That's the current community. The free company's Dropbox, the guy there, he was the first one to run on the all SSD cluster, so he had some really good feedback for us. Germ.io, they're the new company that's doing it's Parquet plus Drill. That's their, I don't know what the business model is actually. Intel, big investor in Cloudera, so they want to see us succeed, and Xiaomi.
So, the question here. When I'm using Spark SQL and Kudu, is the windowing functions and in the SQL all are the higher level, or it doesn't work with Kudu? Windowing function means I want to get top 5 or.
In the basic version that we have of Spark SQL right now, I think it doesn't even push down filters. It's very much in progress. Actually, if you want to help, you're welcome.
So it's at the top level right now.
So it works.
We don't push it down, but it works.
We'll
I mean,
put
it's
a link to the GitHub repo or the Jira's.
well,
for people
actually, it's
who are
going to be
interested.
right there. So if you, if you want to get started as a user, getthrough.io is the website. We also have a user mailing list that's going to move very, very soon to Apache. We also have a Slack room if you want to come chat. We're always there on Pacific time. So if you want to chat in the middle of the night, you might hit one guy from the team. But as the community grows, hopefully we'll have people covering all time zones. There's a quick start VM if you just want to get started without installing all the binaries. We also have, if you're a Cloud Manager user, we have a CSD that's a way to tell a Cloud Manager cluster, like, hey, I have this new service that you can now install, and then it's going to download the parts of Cloudera and install Kudu for you. But you don't need Cloud Manager to install. We also have all the Ubuntu and Rails 6 packages. When I get started as a developer, currently the code lives at github.com/Cloudera/Kudu. Going to move to Apache very soon. All our commits go there first. We're not like shipping things over the wall every time we do a new release. We're completely in the open. And when we opened the repo, not only like we're doing the commits live, we also opened all the commits from back to 2013, so you can see all the dirty laundry on the commits, but also all our Jiras we open sourced, most of them. Those I didn't mention customers. We have a public Garrett instance, so if you want to publish a patch for Kudu, don't do it through GitHub. Go on Garrett, it's going to use your GitHub credentials, and then you can push the patch to Garrett. We'll do the code review there, and Garrett will do the commit. It's a Apache 2.0 license. Obviously, we're going Apache. So if you want to contribute code, you're very welcome. And that's the end of my talk.
Awesome. Good. Give it up.